Yes, same kind of guy. We are still on the DNA cross-linking anti-neoplastics, but specifically we are on the nitrosoureas. Here is what we are going to talk about. We are going to introduce our nitrosoureas. Here in the introduction, we are going to talk about the nitrosoureas. What are they briefly? Then we talk about the general mechanism of action. We talk about the specific agents, but specifically we're going to talk about these three. So the topic is not that much broad, so we can begin now. Nitrosoureas, as the name suggests, they are nitrosoureas derivatives. We are going to see the structures and we see that they are nitrosoureas derivatives. Their structures are very reactive. They have reactive structures which are unstable. They have unstable structures. They are present, some are oral, and we have parenteral formulations. As the name suggests, we say that they are nitrosoureas derivatives. This is the structure of the urea. This is urea. For nitrosourea, this is the structure. This is nitrosourea. So, since they are nitrosoureas, this is the pharmacophore. So, all this determines the pharmacodynamics. So, it is the pharmacophore. Other attachments on these structures, they determine the pharmacokinetics. So, for example, we have the carmustine. This is carmustine. This is carmustine. So, this is the pharmacophore here. This ethyl chloride or the chloroethyl group determines the pharmacokinetics. These two chloroethyl groups. So this is the pharmacophore which determines the pharmacodynamics. When we talk about the romustine, this is the structure. For romustine, this is romustine. This is the structure. So we see the pharmacophore and the substituents here, which determines the pharmacokinetics. This is romustine. We say this is carmustine. When you go to the streptozocin, this is the structure. So we are seeing that what changes are the substituents or attachment to the nitrosourea group. This is the CH3 group. Here we have the NO, but here for it has this group. This is the group we have here, the sugar molecule. At position 2 of the sugar molecule, we have this group. This is position 1, this is 2. This is position 3, we have 4, position 5 and 6. This is streptozocene. So from these structures, we can see that the general structure is this. This is the general structure. That's the general structure from here. And these nitrosoureas, they are bifunctional, meaning that they can alkylate to gain MOHs. After alkylation, we shall have the gain A damage. For the general mechanism of action, we say that nitrosoureas, they are unstable. Since they are unstable, they can decompose in cellular environment. They decompose. We shall have, at first, loss of the proton. This proton from the nitrogen atom shall have proton loss. When the proton is lost, we shall have this. This nitrogen, when it loses the proton, we shall have formation of a bond here. When we form a bond, this bond will break and gives the electrons to the oxygen. So we shall have this with a double bond here. This double bond, we're having the R group this side. Then you have the ethyl chloride with a NO. This is what we have. Since this oxygen is unstable and this chlorine, the chloride atom, is electron withdrawing. So this one will attack this carbocation. When this chlorine pulls the electrons, forms this carbon to be carbocation, then this one attacks the carbon. So we shall have this. The chlorine will be lost to form N. Shall form this with this NO. And here we have the double bond and N with R. This is what we have. The chloride atom is lost. Here we shall have loss of chloride atom or the chloride ion. This is oxazolidine structure. This ring. And this ring will decompose slowly, non-enzymatically. Here we have the hydrogen atom here. This oxygen is having lone pairs of electrons to attack this hydrogen. Then this hydrogen will give the lone pairs of electrons to this carbon here, which shall form a double bond. Then this bond will break and form a double bond here. When you form the double bond here, meaning that this bond will also break. When it breaks, we shall form a bond here. And we have now two structures. One, we have this structure where we have the R, this R with N and double bonds. But we're still having this carbon. This carbon is having this oxygen with a double bond. So we are having this. And this structure is isocyanate. That's one of the metabolites. Then we shall also have this structure where we have this N. This N has formed a double bond with this N. And this N is having oxygen with the hydrogen atom. Of course, this bond will break. When it breaks, we shall have the OH group. By this end is having this carbon. Here we're having a carbon. And this carbon is forming a double bond with this carbon. So we shall have this with H2 and H here. This is vinyl diazotic acid. Then this one will decompose. We shall have loss of the OH group. When you lose the OH group, this nitrogen atom is left unstable. So we shall have using of these electrons to form a bond here. So we shall have loss of OH, this OH, and also loss of the nitrogen as a gas. So we shall have the carbocation, which is CH2, and this is a carbocation. This carbocation can alkylate the DNA. When the N7 of the guanine, which is the nucleophile now, comes, will attack this carbocation. Hence we have the, and this nucleophile is attached to the DNA. Here we have the DNA. Meaning that this one can alkylate the DNA. So we shall have this. You have the DNA. This DNA is on the guanine. And this guanine is attached to the alkyl group, which is the CH2. Again, you can have attacking of the proton, then we alkylate also. This group also alkylates the DNA. Then we have the bifunctional attachment. Then this is one of the pathway. We have the isocyanate. This isocyanate can decompose, but we are going to see it from here because even in the next pathway you can see the formation of the isocyanate. The second pathway, we may have this. When you lose the proton, let me write it. We're having this. When we lose the proton, this proton, we are forming a double bond here. When you form the double bond, this group can break, giving the lone pairs of electrons from here. I mean the bond pairs of electrons to this bond, form the double bond. So we shall have this. Here we have formed the double bond with this N. And this N, when you form a double bond, this one will break. When it breaks, we shall form the O minus. And this O minus can attack the proton and form the OH group. Plus this group here, we have the N forming a double bond with this carbon which is having the oxygen. So we shall form this isocyanate again with R. This is what we have. This is the isocyanate. So we have reformed the isocyanate. This isocyanate can, in presence of lysine, the amino acid lysine, it can be carbamylated to form this. You can form this structure. This is the carbamylated lysine. That lysine. Then this group can again decompose like this one. we can have loss of the OH group. When you lose the OH group, then this nitrogen is unstable, the nitrogen atom. Then you can use these bond electrons from here to form another bond here. So, like this one, we shall lose the nitrogen. Loss of the nitrogen and also the OH group. Then we shall form the chloroethyl carbocation, which is the Cl, this group. This is CH with the CH. This is the carbocation. And this one can calculate the DNA. So we shall have the guanine, which is the nucleophile now. This guanine can attack this carbocation. And may also have the loss of the chloride because it is electron withdrawing group. Another nucleophile comes and attacks this carbon here. So we shall have alkylation of 2DNA with CH with nucleophile on both sides. And remember, these nucleophiles, they are guanine molecules which are attached to the DNA. Even this one is attached to the DNA. So we shall have, this is what we mean when we are talking about the bifunctional ability. Also, this isocyanate can just decompose in presence of water. If you add water, in presence of the water, of course, in the body, may have formation of the carbon dioxide plus NH2 with R from isocyanate. So this is one of the pathway for isocyanate. This is the second pathway. Here we are forming the carbocation, the chloroethyl carbocation, which alkylates the 2 DNA molecules. And here we form the vinyl carbocation, which alkylates the DNA and can alkylate 2 DNA molecules. So these are the 2 pathways for activation and alkylation of the DNA by the nitrosoureas. This is the general mechanism of action. Now, let's go to the specific agents and talk about them. What are they? What can they do? The solubility and also the indication.